Imagine our universe as a gigantic party balloon. Around 13 billion years ago, this balloon was minuscule, practically a dot, containing all the matter of the universe in an incredibly compact space. Back then, the universe was a hot, dense place, vastly different from the expansive, cold cosmos we're familiar with today, with galaxies strewn across an almost unimaginable vastness. The universe's grand transformation from a tiny, hot particle soup to the spectacular starry cosmos we observe on clear nights is a fascinating tale of expansion. Yes, the universe is expanding. Picture blowing air into a balloon, it grows, right? Similarly, the fabric of the universe is stretching, causing galaxies to drift further apart from one another. This phenomenon isn't static. With every passing second, the universe becomes slightly more spacious than it was the moment before. But here lies the mystery that's been puzzling astronomers. At what exact speed is the universe expanding? This question might seem straightforward, but the answer is surprisingly complex. Scientists have been trying to measure this rate of expansion, known as the Hubble constant, but have run into a puzzle. The measurements taken by different methods and instruments, like the renowned Planck Space Observatory, don't match up. What began as a minor discrepancy in 2013 has now evolved into a difference of more than 10% between the measurements. This divergence has plunged cosmology, the study of the cosmos in its entirety, into a sort of crisis. What does this mean? We are faced with one of the universe's greatest puzzles. This mismatch in measurements could hint at new physics lurking, ready to revolutionize our understanding of the cosmos. Day by day, astronomers and physicists around the globe are working to unravel this mystery, bringing us closer to grasping the true nature of our universe. The story we're about to dive into is not just fascinating, it's fundamental to our comprehension of the cosmos. It revolves around a dilemma known as the Hubble tension, a perplexing challenge that currently baffles astronomers and physicists worldwide. Picture two major teams of scientists, each equipped with their own instruments and methods, measuring the same thing: the universe's rate of expansion. However, instead of arriving at the same figure, they find differing values. Even more astonishingly, they're unable to pinpoint the reason for the discrepancy or which of the two values is correct. This is the essence of the Hubble tension. The Hubble constant, denoted by h0, is key to understanding this expansion. Acting like a cosmic ataximeter, it gauges the speed at which the universe is expanding. Yet, discrepancies in its measurements have led to real tension, a deadlock challenging our current understanding of the universe. To appreciate the significance of this issue, let's travel back in time to the 1920s, a period of revolutionary discoveries in astronomy. In this context, two astronomers, Edwin Hubble and Knut Landmark, though working independently, made a startling observation. Not only were distant galaxies moving away from us, but they were doing so in a very peculiar manner. The phenomenon that caught their attention was the redshift. Picture light as a wave that can be stretched or compressed. As a galaxy moves away from us, the light it emits is stretched, shifting towards the red end of the color spectrum. This stretching of light, or redshift, was pivotal to the discovery of the universe's expansion. Hubble and Landmark observed that not just a few, but all distant galaxies exhibited this redshift, indicating they were moving away from us, and more astonishingly, that the entire universe was expanding. This discovery was not only revolutionary but also led to a new way of viewing the universe. The notion that the cosmos was not static but constantly expanding forever changed our understanding of space and time. And today, nearly a century later, we find ourselves on the brink of a potential revolution in cosmology as we strive to resolve the Hubble tension. In this episode, I invite you to dive with me into this tale of discovery, conflict, and relentless pursuit of understanding the cosmos. Let's explore not just the wonders of the universe, but also the curious and determined minds dedicated to unraveling its mysteries. The realization that more distant galaxies are moving away from us at greater speeds was a transformative moment in astronomy. This pattern, far from being a coincidence, provided one of the foundational pillars for the theory of an expanding universe. According to this discovery, not only is the universe expanding, but it does so in a manner that accelerates galaxies the further they are from us. This direct relationship between distance and speed suggests that the universe is not just expanding, but that this expansion has been continuous since the universe's inception. The phenomenon that caught their eye was known as a redshift. Imagine light as a wave, capable of being stretched or compressed. When a galaxy drifts away from us, its emitted light stretches, moving towards the red portion of the color spectrum. This elongation of light, or redshift, played a crucial role in unveiling the expansion of the universe. Hubble and Landmark noted that not merely a handful, but all distant galaxies they observed showed this redshift, signifying they were receding from us, and, even more remarkably, that the entire universe was in a state of expansion. This breakthrough was not just revolutionary but also introduced a new perspective on the universe. The idea that the cosmos was not static but in a state of constant expansion radically altered our perception of space and time. Now, nearly a century later, we stand at the threshold of potentially another major shift in cosmology as we endeavor to untangle the Hubble tension. In this episode, I welcome you to join me on a journey through this narrative of discovery, conflict, and the unyielding quest to comprehend the cosmos. We'll delve into not only the universe's marvels but also the curious and resolute individuals who devote their lives to deciphering its enigmas. The observation that galaxies further away from us are receding at higher velocities marked a pivotal moment in astronomy. This pattern, far from coincidental, laid down one of the critical pillars for the theory of an expanding universe. This finding implies that the universe is not only expanding but does so in a way that accelerates galaxies the more distant they are from us. This correlation between distance and velocity indicates that the universe's expansion is not a recent occurrence, but has been ongoing since the universe's very beginning. In this episode, we'll delve into the fascinating realm of cosmic candles and uncover how they've illuminated our path to understanding the vast scales and incredible dynamics of the universe. We'll explore how, through these observations, scientists are striving to unravel the secrets of the universe's expansion, tackling the challenges posed by the Hubble tension and seeking answers to some of cosmology's deepest questions. Our journey together, crossing the vast expanses of the cosmos, now leads us to a deeper understanding of how we measure astronomical distances, a crucial component in resolving the Hubble tension. Imagine we're trying to figure out how quickly the universe is expanding. For this, we need two fundamental pieces of information: the distance of galaxies from us and the speed at which they're moving away. The beauty of this investigation lies in how we obtain this information. Let's start with the question of distance. In the vast theater of the universe, standard candles are our spotlights, astronomical events whose brightness we know with great precision. Type Ia supernovae are the stars of this show. These stellar explosions occur in a peculiar binary system, a common star and its companion, a white dwarf. The white dwarf, a stellar remnant that has exhausted its nuclear fuel, is sustained against collapse by electron repulsion. The dynamic begins when the white dwarf starts to steal mass from its stellar companion. However, this greed has a limit. When too much mass is accumulated, gravity overcomes electron repulsion, leading the white dwarf into a catastrophic instability, resulting in a supernova explosion of unimaginable magnitude. The key for us, observers, is that each Type Ia supernova explodes with the same intrinsic brightness, acting as a lamp with a known wattage, shining across the cosmos. This uniformity in the light emission from Type Ia supernovae allows us to use them as distance metrics. By knowing how bright the supernova should appear and comparing it to how bright it appears from Earth, we can calculate its distance. And, by extension, we determine the distance to the galaxy that hosts this supernova. But it's worth noting, Type Ia supernovae are just one type of standard candle. Modern astronomy doesn't put all its eggs in one basket. There are other cosmic events and objects that serve similar purposes, each with their peculiarities and unique contributions to our understanding of the universe. By mastering these measurement techniques, we better equip ourselves to unravel the mystery of the universe's expansion. This knowledge not only brings us closer to resolving the Hubble tension, but also allows us to appreciate the ingenuity and creativity of humans in the quest to understand the grand spectacle of the cosmos. As we explore these concepts, it's important to remember that we're at the frontier of knowledge, witnessing and contributing to the history of science in real time. After determining the distance to galaxies using standard candles, our next challenge is to measure the speed at which these galaxies are moving away from us. This measurement is crucial to unraveling the mysteries of the universe's expansion and gaining a better understanding of the Hubble tension. To accomplish this feat, we turn to a fascinating principle from Einstein's theory of relativity, redshift. Imagine a star emitting perfectly white light. If this star moves away from us at a considerable speed, the light we perceive will no longer be white, it will tend towards red. This phenomenon is known as redshift. Conversely, if the star approaches us, its light will appear bluer, a phenomenon called blue shift. This color shift is subtle, especially for speeds not approaching the speed of light, but with the precision of modern astronomical instruments, we can measure this variation with great accuracy. Stars, these giant spheres of incandescent hydrogen, serve as natural physics laboratories. We know precisely the type of light hydrogen emits. By comparing the observed light from stars in distant galaxies with the light we expect hydrogen to emit, we can identify the redshift. This shift provides us with a direct measure of the galaxy's relative speed to us. The greater the redshift, the faster a galaxy is moving away from us. This leads to one of the most astonishing discoveries in astronomy: the relationship between a galaxy's distance and its speed of retreat. This relationship, reflecting the universe's expansion, was first observed by Edwin Hubble, hence the name of the Hubble constant, h0, that describes this expansion. By combining these two methods, using standard candles to measure distances and redshift to measure speeds, we can map the expanding universe. These observations are key to understanding how the universe expands and solving the Hubble tension. As we refine our techniques and instruments, we draw ever closer to understanding the most intricate details of this grand cosmic ballet. It's a journey of discovery, where each new piece of the puzzle brings us closer to unraveling the mysteries of the universe. The beauty of science lies in its ability to decipher the universe's mysteries with methods that might seem almost magical at first glance. The relationship between the galaxy's recession speeds and their distance from us is a perfect example of this magic. When we look up at the night sky, we're not just admiring points of light, we're observing a constantly expanding universe, where distant galaxies move away from us at speeds that increase proportionally with their distance. This linear relationship is represented by a line known as the Hubble law, with the Hubble constant, h0, serving as the slope of this line. And here we encounter the fascinating concept that transformed our understanding of the cosmos. Galaxies that are twice as far away tend to move away twice as fast. The Hubble constant, estimated at about 73 kilometers per second per megaparsec, gives us the rate of the universe's expansion. This means that for every megaparsec, about 3 million light-years of distance between two galaxies, they move away from each other at a speed of 73 kilometers per second due to the expansion of the universe. It's a concept that's both simple and revolutionary, aiding our understanding of the cosmos's dynamics on a grand scale. Now, let's dive a bit deeper and understand how this measurement conflicts with other approaches. The Hubble tension, at the heart of this dilemma, emerges when we compare the value of 73 kilometers per second per megaparsec with measurements derived from observations of the early universe. The Planck Space Telescope, for example, studied the cosmic microwave background, CMB, the leftover light from the moment the universe first became transparent, allowing light to travel freely. This study of the CMB provides a window into the universe's beginnings, and the measurements derived from these observations suggest a different value for the Hubble constant, intensifying the tension between the two approaches. It's this quest for understanding, this journey to resolve contradictions and expand our knowledge, that makes astronomy and cosmology such thrilling fields. Each new piece of data, every new observation, brings us closer to understanding the mechanisms governing the universe, even as we find ourselves facing more questions than answers. So, if you're captivated by these revelations about the universe, the constant changes in science, and the adventure of unraveling the cosmos's mysteries, make sure to subscribe and follow along. We're all in this journey of discovery together, learning new things every day, not only expanding our understanding of the universe but also our curiosity and awe for what lies beyond our reach. The moment when the universe became transparent, about 380,000 years after the Big Bang, marks a turning point in our cosmological understanding. The light emitted at that instant still travels through the cosmos, reaching our telescopes as the cosmic microwave background, CMB, a relic from the universe's youth, a kind of luminous echo from the cosmos's earliest moments. For those who delight in the night sky, imagine being able to observe not stars or galaxies, but the very primal light of the universe stretching across the firmament in microwave wavelengths. According to the Lambda CDM model, the early universe was a hot, dense soup of elementary particles and radiation. As the universe expanded and cooled, structures began to form from slight irregularities in the initial distribution of matter and energy. Dark matter, which does not interact with light but exerts gravity, played a crucial role in clumping normal matter, atoms, around it, leading to the formation of the first stars, galaxies, and galaxy clusters. The Lambda CDM model has been extraordinarily successful in explaining the appearance of the cosmic microwave background, as well as the large-scale distribution of galaxies in the universe. However, like any good scientific model, it is constantly tested against new observations and measurements. The Hubble tension, for example, is a current challenge for cosmologists, requiring them to refine their models and, perhaps, even discover new physics. The beauty of science lies in its relentless quest to understand the universe, a journey that takes us from the depths of space to the furthest reaches of human knowledge. By looking at the CMB and understanding what it reveals, we are reading the first pages of the universe's history, a captivating narrative of origins and evolution that still has many chapters to be discovered. The Lambda CDM model is like a key attempting to unlock the deepest mysteries of the universe, from its explosive birth in the Big Bang to its vast and complex state today. This model, with its primordial soup of cosmic ingredients, matter, including the atoms that make us, highly energetic radiation, dark matter, an enigmatic form of matter that does not interact with light, making it invisible, but whose presence is inferred through its gravitational effects, and dark energy, the mysterious force behind the universe's accelerated expansion, provides a framework for understanding how the universe evolved and structured itself into galaxies and other celestial formations. Dark energy, symbolized by the Greek letter lambda, in the model's name, and cold dark matter, CDM, are two of the most intriguing concepts in modern cosmology. Despite not fully understanding what they are or how they work, their influences are undeniable in current theories about the universe's structure and evolution. And regarding the temperature fluctuations in the cosmic microwave background, CMB, these subtle variations that we map in the night sky tell the story of the universe's earliest moments, 380,000 years after the Big Bang, when the universe became transparent, and light could travel freely through space. These fluctuations, though seemingly random, are the echoes of complex physical processes that occurred in the universe's infancy. The Lambda CDM model helps us interpret this pattern, linking the temperature fluctuations we observe today to the universe's initial conditions. According to this model, the temperature fluctuations in the CMB can be attributed to three main sources. 1. Quantum fluctuations * in the extremely dense and hot early universe. Small quantum variations were amplified by cosmic inflation, a period of exponential expansion that occurred fractions of a second after the Big Bang. These fluctuations became the seeds of future galaxies and cosmic structures. 2. Matter and radiation interaction * as the universe expanded and cooled, matter, primarily hydrogen, began to form the first atoms. During this process, matter intensely interacted with radiation, creating a pattern of fluctuations that reflects this interaction. 3. Effects of dark matter * the gravity of dark matter began to pull normal matter together, forming the first cosmic structures. This distribution of matter affected how the cosmic microwave background radiation propagated through space, contributing to the pattern of fluctuations we see today. By understanding these origins, we can appreciate how the Lambda CDM model provides a comprehensive explanation for the current shape of the universe, from the grand galactic structures to the tiny details mapped in the cosmic microwave background radiation. This is just a glimpse of what modern cosmology can reveal to us about the universe. And if there's interest in delving even deeper into the mysteries of dark energy, it's a fascinating path filled with discoveries waiting to be explored. I encourage everyone to get involved, ask questions, and, of course, keep following for more explorations of the cosmos. The Hubble tension, this discrepancy between the values of the Hubble constant obtained by different methods, stands as one of the most fascinating puzzles in modern cosmology. Shockwaves in the primordial plasma, low-density regions created by radiation winds, and the uneven transition of the universe from an opaque to a transparent state, all play crucial roles in the temperature fluctuations observed in the cosmic microwave background, CMB. Each of these cosmic events leaves a distinct mark on the CMB, creating a pattern of disturbances whose size and intensity vary. This pattern is an echo of the early universe's conditions and offers clues about the universe's expansion rate. Understanding these origins allows us to appreciate how the lambda CDM model offers a comprehensive explanation for the current shape of the universe, from grand galactic structures down to the minute details mapped in the cosmic microwave background. This is just a glimpse into what modern cosmology can reveal about the universe. And for those interested in delving deeper into the mysteries of dark energy, it's a fascinating path filled with discoveries waiting to be explored. I encourage everyone to get involved, ask questions, and, of course, continue following for more explorations of the cosmos. The Hubble tension, this discrepancy between values of the Hubble constant obtained by different methods, stands as one of the most fascinating enigmas of modern cosmology. Shockwaves in the primordial plasma, low-density regions generated by radiation winds, and the uneven transition of the universe from an opaque to a transparent state, all these phenomena play crucial roles in the temperature fluctuations observed in the cosmic microwave background, CMB. Each of these cosmic events leaves a distinct mark on the CMB, creating a pattern of disturbances whose size and intensity vary. This pattern echoes the conditions of the early universe and provides clues about the rate of the universe's expansion. What's interesting here is that the fluctuations in the CMB don't just give us a picture of the young universe. They also provide a means to calculate the Hubble constant, h0, in a way completely different from standard candles. This calculation based on the CMB and the physics of the early universe suggests a value of 67.7 kilometers per second per megaparsec. Comparing this with the value of 73 kilometers per second per megaparsec obtained through standard candles, we find a notable difference of about 10%. This leads us to the heart of the problem. The Hubble constant, by definition, should be constant. There shouldn't be two values for h0 if we're talking about the same rate of expansion of the universe. Initially, many in the scientific community thought this discrepancy might be explained by an error in measurements. Perhaps one of the methods was flawed, or maybe both had their inaccuracies. However, as measurement techniques were refined and new data were collected, the likelihood of a simple error became increasingly improbable. Moreover, new ways of measuring h0 were developed and, intriguingly, also showed this tension, reinforcing the idea that we are facing a true scientific puzzle. What does this mean for cosmology? We're faced with an exhilarating situation. Either there's something fundamental we don't understand about the universe, or we might be on the verge of a new discovery in physics. Either way, resolving the Hubble tension is not just about correcting a number in a textbook. It's about refining our understanding of the cosmos, exploring potential new physics, and perhaps even redefining our view of the universe. This field is constantly evolving, and each new piece of data, each new analysis brings us closer to understanding not just how the universe is expanding, but also why it expands in the way that it does. So, as we delve into these profound questions, I invite you to stay curious, engaged, and always ready to question what we think we know. After all, it's this unending curiosity that propels us forward, in search of the answers that define our understanding of the universe. This division in the methods of measuring the Hubble constant, h0, highlights one of the most intriguing and challenging questions in contemporary cosmology. On one hand, we have measurements based on the current universe, through objects like standard candles and the movement of galaxies. that suggest a value around 73 kilometers per second per megaparsec. On the other hand, methods that look back in time to the primordial universe, using data like the cosmic microwave background, point to a lower value, about 67.7 kilometers per second per megaparsec. The persistence of this discrepancy, even with the refinement of techniques and the accumulation of data, indicates that we are not dealing with trivial experimental errors. In fact, the discrepancy remains robust against the possibility of multiple systematic errors in multiple experiments, which would be statistically improbable. Faced with this deadlock, the scientific community finds itself at a theoretical crossroads. If the experiments, refined and repeated countless times, are not the source of the problem, then the most plausible explanation lies in the physical theories underlying these measurements. Herein lies the beauty and complexity of science. The constant quest to understand reality leads us to question and, when necessary, revise our most fundamental understandings. The measurements of the current universe, which give us the Hubble constant of about 73 kilometers per second per megaparsec, are based on our understanding of relatively well-understood astrophysical phenomena, such as the properties of stars and galaxies. In contrast, the measurements that look back at the primordial universe, offering a lower value for H0, rely on theories that encompass quantum physics and the cosmology of the earliest times, a territory still filled with uncertainties and developing theories. This situation suggests that either our understanding of the current universe is incomplete or misinterpreted, or our theories about the primordial universe need adjustments, or possibly, both scenarios are true. Resolving this tension will not only profoundly affect our understanding of the universe's expansion but may also unveil new physics, or phenomena not yet contemplated by current theories. The quest for a solution to this puzzle is one of the most active and exciting fronts in modern cosmology. It invites us to reconsider what we know about the universe and to explore new ideas and theories that might reconcile these discrepancies. The path forward may require new physics, perhaps involving even more exotic concepts like unknown particles, extra dimensions of space, or even a new understanding of dark energy and dark matter. This is an open invitation to imagination, innovation, and discovery at the frontier of human knowledge. You've just provided an engaging and insightful summary of the current situation in cosmology, capturing perfectly the essence of the dilemma faced by scientists. The Hubble tension isn't just a technical problem to be solved. It represents an invitation to deeper reflection on the fundamentals of physics and our understanding of the universe. What makes cosmology so thrilling is precisely this constant state of evolution. Science, at its core, is a dynamic process, always open to revisions as new information and technologies become available. The Hubble tension illustrates this process in action, challenging established theories and prompting the scientific community to seek deeper answers. The discrepancies between measurements of the current universe and the primordial universe are not just diverging numbers. They are clues that might lead us to a richer understanding of cosmic reality. We may be on the verge of discovering new particles, forces, or even fundamental principles of nature. Or, perhaps, the solution to this tension lies in a new interpretation of already known data, an adjustment in our existing theories that allows us to see the universe in a completely new light. Regardless of what the answer might be, the journey to unravel this mystery is as important as the final destination. It compels us to question, experiment, and learn, the pillars upon which science is built. As we navigate this uncertain path, every discovery, every moment of understanding, brings us a bit closer to the truth, expanding not just our knowledge of the cosmos but also our sense of wonder and admiration for the universe we inhabit. So, yes, we are faced with a challenge, but also an incredible opportunity. The Hubble tension is a reminder that, at the heart of science, there's always more to discover, more questions to ask, and always more horizons to explore. Your enthusiasm for the challenges and opportunities presented by the Hubble tension is absolutely infectious, and reflects the excitement many in the scientific community feel. We are indeed at an extraordinary crossroads in cosmology, where inconsistencies are not merely obstacles but beacons that may light the way to new discoveries. The possibility that both our models of astronomical objects like supernovae and galaxy movement, as well as our understanding of the primordial universe, need to be revised is a reminder of the ever-evolving nature of science. Each adjustment in our theories, every new hypothesis we explore, opens doors to a deeper understanding of the cosmos and our place within it. The notion that we need some kind of new physics to resolve the Hubble tension is not just a challenge, it's an invitation to creativity, innovation, and intellectual exploration. Whether it's revealing new properties of dark matter and dark energy, discovering entirely new forms of matter, or even rethinking the fundamental principles of physics, we're on the verge of potentially revolutionizing our understanding of the universe. History shows us that it's in times of great challenge that science makes its most significant leaps. Edwin Hubble's discovery of the universe's expansion radically transformed cosmology, and now, the tension surrounding the constant that bears his name may be setting the stage for a comparable breakthrough. Your final message perfectly captures the wonder and gratitude of living in such an exciting time for science. With each new discovery, with each challenged theory, we expand not only our knowledge but also our capacity to marvel at the universe. Being alive in an era of such discoveries is undoubtedly a privilege. Thank you for sharing this inspiring perspective. Until next time, may we continue together on this journey of discovery and awe.